Welcome, and I'm Gwen Bell, director of the museum, for those who don't know me. This is the one unique lecture this spring that we videotape, and it is our way of sharing with others what some people do as oral history and only have a few invited people in a room. We think it's rather nice to let people tell their story for a group of those who are interested, and this is very important for the archives of the museum. And there are two pioneers here tonight. There is Morris Wilkes, who opened the museum with his first lecture, but he's really known because he built the first stored program computer that was full-scale and operational, and is a very old friend of Jan Rajchman. They were both building and in the computer game together in the 50s, and I will ask Morris to introduce Jan Rajchman.
Thank you, Gwen. Yes, indeed, I've known Jan Rajchman for a long time. I first heard him lecture at a course that was held at the Moore School of Electrical Engineering in Philadelphia in the summer of 1946. It's a course that has become quite famous. I arrived very late and missed a certain amount, but I'm very glad to say I didn't miss Jan's lecture. He spoke about the Selectron, which was a vacuum tube for storing information. It was fascinating to me. The principle on which it worked was new to me, and I admired the ingenuity of coding of information, coding of the addresses. Now, some of you may think that pin limitation was something that hit us with semiconductors, but I can assure you it started with vacuum tubes. And then I remember going to see Jan at the RCA Laboratories in Princeton in the early 50s, about 53 it may have been, and he was working on core memory by that time. I remember he had a matrix of 100 by 100 cores. It's rather original to have a decimal number instead of a binary one. And these cores could all be written into and accessed except one. And I remember him pointing out that they had discovered that that one was missing, that the man who made the matrix had forgotten to put it there. So that was all right. And then I remember on that occasion, when we were having lunch, Jan said to me seriously, did I think that programmers would ever want as much memory as 10,000 words? I of course gave the right answer. But there was a view then, I'm sure it wasn't held by Jan, put forward by people like von Neumann, who said that little core memories were the thing, provided that you had a magnetic drum to back it up. The RCA at that time, as a result of Jan's work, were very well ahead with core memories, and I've often wondered why they didn't press it. Perhaps it was a feeling of doubt as to whether the core memory was ever going to be a commercial success. Then I used to meet Jan at conferences. I always used to look forward to those meetings. We would go into a corner somewhere and discuss the state of the technology. Jan always had the latest information and would pull out of his attaché case little demonstration models, little bits and pieces from his own lab, illustrating the work that was going on there. And as I say, I look forward to those meetings, which I found were of absorbing interest. Well, tonight, he's going to look back over the past and tell us about it. And I think this lecture also is going to be of absorbing interest. Yeah.
Thank you. Thank you very much, Morris. I certainly remember also the many times we met this side of the Atlantic or the other and had many discussions. I would like to start by saying that I don't pretend to be a historian, and it's very difficult to piece together everything that happened in computers in the early days, and of necessity I'll speak from my own recollections the way things happened to me, and I don't pretend that this is by any means a general description of what happened in the old days. The way we entered the computer field at RCA in 1939 was due to a visit of a colonel from the US Army who said that the Germans had a great superiority in the air and the Allies have very poor anti-aircraft guns to shoot at them, or rather the control of the guns was very poor, and the mechanical so-called directors that were made to direct the gun were utterly too slow. They had been designed for ships and tanks, but for airplanes they were very much too slow. So this colonel said, I don't know anything about electronics except it's fast. And so why don't you people try to do something about that? So the job was assigned to me, and my natural inclination was to look at how the job was done mechanically, because it was in fact a very ingenious machine. And my first inclination was to simply do this electronically in the same way, namely in an analog fashion. But I soon discovered after a few months that doing anything analog at high speed was very difficult. That is, to simply add two quantities or multiply two quantities with a precision, say, of 1% was already very difficult when it was simply DC. But if you want to do this at any speed, it was nigh impossible. And obviously, we needed precisions much greater than that. So very soon, I switched to the digital approach, and obviously, we used the binary system as an obvious, natural thing to use. And we developed, and I say we because very soon I was joined by other people in the laboratory, developed various arithmetical units. We made shift registers, we made adding devices, multipliers, dividers, and we even made what is now called a read-only memory, and which in those days we called an arbitrary function generator, and which I may say a few words at the very end if I have time about that development. But it became also evident that the digital techniques would require many, many tubes, that they would be very bulky, and it would take an enormous amount of time to develop an anti-aircraft fire control. But fortunately at that time, for our techniques, it developed that ballistic tables had to be calculated, and generally guns were being developed faster than ballistic tables could be printed and calculated for them, and so there was a dire need to do that. Well, now for that applications, then a very huge machine that wouldn't have to be portable in one central place would be all right, even if it was very expensive. So that was the origin of what became the ENIAC. Actually, there is some question as to whether the ENIAC could have been undertaken by RCA or the University of Pennsylvania. Actually, we had already done more work than they had done at the university by that time, which was, I think, 40 or thereabouts. However, RCA, frankly, had cold feet. RCA considered that, not I, but some of the people who had the power, I was a very young man at the time, considered that any machine that would have 40,000 tubes would be a monster that would never work, and that wasn't the business of RCA. So that, in effect, we turned down the job of building the ENIAC. However, as Boris just mentioned, we were asked to tell everything we knew, and of course there was a patriotic atmosphere at the time, and so we went to the University of Pennsylvania. We told them absolutely everything we knew, and I went there many times, and some of the things we had developed were used, notably the read-only memory that I mentioned at the beginning, and also a decimal ring counter. Well, as is fairly well known, the ENIAC was first destined to make these ballistic tables, but soon afterwards it became apparent there were other problems that are a higher priority, and I learned, of course, after the war that there were some questions relating to the atomic bomb that had to be calculated, and it took priority. And so the question was to change the design of the machine from one problem to another. The idea being that if you want to solve a problem, well, tell me what the problem is, and I'll build you a machine to solve it. And so the idea was, well, we've done it partially for this problem, now we need another problem, and so why don't we put the connections that decide what problem you solve on patch cords. And then when you want to change the problem, well, you just change the patch cords the way you change telephone patch cords in an old manual telephone exchange. And then people said, well, why not we put relays rather than patch cords? And then, well, why if you put relays, you have vacuum tubes every place else, why don't you put vacuum tubes? And then very slowly, but very slowly, the idea of the stored program evolved. That is to say that you can make a machine for any problem at all that you don't know in advance, and that later you program the machine to actually solve the problem. Well, skipping over all of this, which takes surprisingly longer time than people think, because today the idea of the stored program is taken for granted as a sort of a gift of nature practically, but actually it took some time to really have it in the very simple form that we have it today. Well, what was missing, of course, was the memory, because obviously a stored program computer has to have a memory to accept the data on which you do the calculation as well as the program. So one of the first ideas was if I just push the button, right, was the idea of using a delay line in which you put a train of pulses on the input and you make them go through a delay line, you detected them on the end, and you put them back through the delay line. So as soon as you put a disturbance in here, it sort of went across it and came back, and then you could put as big a train of pulses as you needed. This was an idea that I believe Eckert proposed. And the beauty of this is, of course, that you don't construct the bits. The bits are a mere disturbance, which happen to be a pole of mercury, or it could be a magnetostrictive line that travels along, but you don't build it, it doesn't cost any money. And therefore you can make a very long delay line at a low expense, and the only thing you need is all this electronics, which isn't very much. Now, by the same token, the more memory you have, the longer you have to wait for any one bit that may be of interest. And so if you have a stored program computer and you need to jump from one instruction to another, then you have to wait until the delay line will produce that bit. And so the people were very itchy, and they said, well, we would rather like to have random access to it rather than the serial access of the delay line, and so the word random access was born. Actually, at the time, I was very unhappy about the choice of the word, because there's nothing random about the random access memory. You select exactly the address you want, and there's nothing random about it. But the word random came from the fact that prior there was a serial line. And the word, just to say again, I also didn't like the word memory because it implies that it has some intelligence. Having memory in animals is more than a store, and I rather like the more sort of succinct way that the British call this a store of information. It's really a selective store of information. An addressable store of information is really the name. However, the name random access memory has, of course, stuck. Well, now, after the war, von Neumann, who was the great proponent of the stored program computer by then, decided to have a machine built at the Institute for Advanced Study in Princeton. And since we were in Princeton, they asked RCA Laboratories to cooperate with him and to undertake the building of the memory. Well, now, how can one build a memory? Well, in those days, of course, cathode ray tubes were making possible television and displays of all sorts, and it was natural to simply orient an electron beam on a screen and then deposit a positive or a negative charge, and then come back to that point and decide whether the charge was there or not. And of course, to do that, you have to have a digital to analog converter to deflect the beam, and then you have to have some kind of a mechanism to store the charge. Well, if you look at the picture of the screen, you could put a little screen in front of the actual insulating part of the normal phosphor screen of a cathode ray tube, shoot electrons at it, and then it turns out that when you shoot electrons at the screen, the particular surface will either go positive or negative. Now you think it would go negative, and so because electrons are negative, and indeed it does if the original potential of the screen is not very high. However, if the potential is reasonably high and the electrons impinge at a fairly high velocity, then secondary electrons are produced, and in fact there may be more secondaries than primaries, and therefore the screen goes positive. And in fact, the current voltage characteristic then is first negative, if the current is negative, then it gets to be positive. Now, if the screen becomes more positive, that is the area that's bombarded, more positive than the accelerating screen, then the secondary electrons can't escape, they're suppressed, and therefore the current goes negative again. So therefore there are three values for which the current is zero. And it turns out that those two are stable, that is, if the screen happens to be that potential, they remain that way, and this one is unstable. And so this is a natural way then of storing a 0 or a 1. And there were a number of projects that used the cathode ray tube, and they used a flood gun to keep any place that was positive was kept positive, anything that was negative was kept negative. And then by overwhelming the stability of it at one point, one way or the other, one could write plus or minus. I don't want to go through all the details of how this was done. However, it was found that unless the target was divided physically, the positive or a negative element, the boundary between them would move in uncontrollable ways. And by the way, I would, since there are eminent Britishers with us, I will say that when Turing first visited us in the laboratory and I explained this to him, he predicted that this would happen, which I thought was rather interesting. Anyway, the fact is that one had to make structure. In other words, put little pieces of metal that could be plus or minus, and another piece of metal plus or minus. And there was a project, for example, at MIT that was based on a tube of that kind. Well, now the problem with making structures in tubes is that it's a fairly complicated affair. You know, the vacuum technology is not such a simple thing. And so Professor Williams at Manchester thought that maybe he could get away with no structure at all, and in fact take advantage perhaps of the instabilities that were noticed here. And he imagined the idea of using a perfectly ordinary cathode ray tube with the only thing was that its face was painted with metal, and then when he bombarded a certain area, the secondary electrons went away to the walls of the tube, so the area became positive. And so that if you went to another position, it simply remained positive by the fact that the insulation was good enough. On the other hand, if he came at this point and he deflected the beam just by a beam diameter, he would write a bigger spot. Well, now, to interrogate the position, you deflect the beam by 1 diameter from the original position. And now, if the screen was originally positive, nothing will happen because it's already at the potential that to which it should be established. On the other hand, if it wasn't wiggled before, it would go positive and induce a slight signal on the back plate. So that was a very ingenious idea because you could then use ordinary tubes that you didn't have to fabricate. And by the way, in the British economy, the way it was, that was a great advantage, I imagine. And but it had the extraordinary disadvantage that the signal was exceedingly weak, so weak that you had to shield the tube with enormous precautions. Otherwise, a trolley going by would completely spoil your signals. And furthermore, it turned out that the analog to digital deflection was very difficult because not only you had to hit the spot exactly, but you had to also have this miniature excursion. So it turned out it was a tour de force. And so that I, for one, was I thought this was not the way to do digital things. This was analog techniques to the nth degree, extremely ingenious. By the way, this was Professor Williams' tube idea came after the idea of the Selectron, which I now will come to. Now, the idea of the Selectron is simply that if you are going to be in the digital world, darn it all, build it. Build a grid, XY grid, and then then when you open a particular window, why the electrons will go there and nowhere else. There is no uncertainty about digital to analog deflection. Well, as Morris pointed out at the beginning, of course, if you make many wires, one way or the other, then and if you have to put them through the vacuum, through the base, this is of course a pin problem that existed then, and even more so because you have to go through a vacuum envelope. So the idea of the Selectron was sort of the idea of a picket fence. If you have a picket fence and you bombard electrons and you can make a wire positive or negative, if 2 wires are positive with respect to the cathode, the electrons will go by inertia in between. However, if you make 1 positive and 1 negative, an electron that comes in between will be blocked, or you can arrange the geometry so it will be blocked. Well, now it means that in the 1 dimension, you have a 2-dimensional selection, because I can connect this wire to this wire and this wire to this wire in some combinations in such a way that I only have the square root of the number of combinations. And there are lots of ways of doing that. I won't bother you with telling you how all this was done. So the idea is you bombard everything, and then you by putting these wires negative, it comes to only to 1 point. However, in the normal storing condition of the tube, you utilize the fact that current is available all over, and you make all the wires positive and bombard the target. Here are the cathodes. Here are the vertical selectors, and there were wires like this for the horizontal selection. Well, now we put a concrete device at every point, an eyelet, which was actually machined, and this eyelet then will assume one or the other of the 2 potentials, stable potentials. The electrons hit it, and the secondary electrons are collected by this plate, then it's positive, or else the electrons try to hit it, but can't do it, and the electrons go back to the cathode. Now, to show this in somewhat greater detail. I think I have it. Oh, well, the other point was that normally all the currents was on, and so each one of those islets was maintained at a positive or negative potential. However, when you wanted to write, you stop the current in all but one, and then by putting a pulse of voltage on a plate in here, you could force the element by capacitive action to go to one potential or another, and then it would lock, it would latch. But now, how do you know whether it's positive or negative? After all, each of those elements is floating, there are no leads to it. Well, the way to do that was to make a hole in it, and if the element was positive, then the current went through, but if it was negative, it was stopped. Well, now, so the current went through, and then just for fun, we also made it possible to view what you stored by putting a phosphorescent screen, and then take the secondary electrons from the phosphorescent stream and collected them, and that was the signal. And at the same time, the signal lids were put in a Faraday cage, so they were not sensitive to any disturbances from the outside. And so that this is, as I said before, if you artificially vary the potential of this element, then the current voltage characteristic is like this. In other words, it becomes first it becomes negative, you attract electrons, then secondary electrons start. Here secondary emission and primary emission are equal, then secondary emission dominates, and then if you make it more positive than this plate, then the secondary emission is suppressed, goes negative again, and here are the two stable points. And this is all the details of how this was written and so forth. I won't go through all of that, but I'll simply say that the cycle time was 20 microseconds, which in those days was considered to be very fast. But of course today people would laugh, it's practically an elephant pace. The next slide is a picture of the tube, which is in fact exhibited in this museum. And the next picture shows the monstrous circuits that were required to drive them. Here you have 20 tubes, and all these circuits and kilowatts of powers coming in and so forth. This is a picture, this is a test setup that we built at RCA Laboratories, but it's not much different from the Johnniac that was built with Selectrons later on. In some sense, the Selectron can be viewed in the modern parlance as an integrated vacuum technology. And I'll say that we thought of many other integrated vacuum technologies. For example, we thought of a completely binary unit that would multiply and add, that was also built completely by means of secondary emission stunts with many floating electrodes that influence one another. The Rockefeller Foundation at the time, not Rockefeller, Warren Weaver, who was the head of one of the committees of the Department of Defense, who later became at Rockefeller Foundation, was very taken by that idea. Gave us a contract, and we actually built part of that tube. However, the vacuum integrated technology was not a good idea because it requires too much of a pre-design. That is, you had to decide exactly what logic you are going to build to do it. And of course, obviously, the art of the progressed so far that you always had new ideas in logic, and it wasn't a good idea. But anyway, it was vacuum integrated technology. Well, now the core memory, about which I'd like to say some words, was conceived independently at MIT by Forrester and by us at RCA, and there was a famous patent suit, and I won't go through any of that. But the fact is that we actually, at the time, were great cooperators and worked together and trying to help each other. But I will just say a few words about the idea. If you take a a little core of magnetic material, it may have a square loop. That is to say, the induction or the magnetic flux around it as a function of the electromagnetic force that you drive would have an almost square characteristic. In general, it's a more curved characteristic that looks like an integral sign. Well, now if you put a very strong current, say in the positive direction, then the magnetization goes like this, and then when you come back to zero, it stays here. On the other hand, if you put a very negative current, it will go like this, and it will stay here. So it will stay naturally in one or the other of the two states, and that's, in a sense, a gift of nature. The magnetization is one way or the other, and it stays that way for free. Well, now the main question is that if you have many of these, then in an array, then you like to have one change but not the others. And so the idea is that you put a current that tries to drive it positive, only half the value that's required to turn it over in one wire, and then it's half in the other. And if you put them together in coincidence, well, they will switch the core. But the trick is that they shouldn't switch any other core. You want to switch this one, but no other. And therefore, if the loop was not square, if the loop was, say, like this, then in fact you would change it, and you would gradually demagnetize the cores, and you wouldn't keep it. So in order for this to work, the hysteresis loop has to be square. By the way you read it is that you attempt to make it say positive. If it was already positive, nothing happens. On the other hand, if it was negative, it will switch and thereby induce a voltage in a wire that links them all, and you'll notice that there is a voltage on it. And of course, the act of reading is so-called destructive. You've destroyed the information by reading, but that's no great pain, because you know that you've destroyed it since you have a signal, so you rewrite it right away. So that's briefly the principle of the core memory. Well, now, speaking for myself, I don't remember a day when I didn't think of it. I mean, I always thought of the core memory. The only thing is that there were no, to my knowledge, magnetic materials that had square loops. And to my great amazement, one day I was reading a magazine, and I found that the Germans had developed a square loop material of very thin permalloy that they developed for making magnetic amplifier for submarines. One of the few electronic successes of the Germans that were really superior to the Allies. And it turned out that Armco Corporation got the patents from the Germans, and they were making these loops. And so I said, oh, but gee whiz, well, that's it, then we have the memory. And so it turned out they were in Philadelphia, not very far, and we got some bobbins. And by the way, the MIT group went through exactly the same process. They also found the same people in Philadelphia, and they got the same bobbins as we did. And so we made these bobbins. However, these bobbins were very expensive. That is to say that we were paying like $10 a bobbin. And that was because they were just trying to encourage us. It cost them much more to make them. So it was obvious that that wasn't a good way eventually. And it was obvious, at least to me, that the way to do it was to use ferrite, because ferrite is dirt cheap, and of course it's used to make television yokes. RCA makes it by the ton. And so I asked some of the people who had developed ferrites, who didn't want any hysteresis loop at all. They wanted a straight line, because as is well known, the hysteresis loop produces heat losses. And of course they didn't want that. And so all their skills were used to make no loop at all. So I asked them, well, could you make a square loop? And to my great amazement, in 6 months, they synthesized a material that had a square loop. And it turned out there were, in fact, many materials that had them. So we immediately made the cores and that you compress like aspirin tablets in an automatic pressing machines. In fact, we bought a machine for that are sold to the pharmacists for making tablets, and we simply modified it to make the cores, and the thing worked right away. Now the idea that I just mentioned at the moment is this idea, that is, you excite X and Y, you have a winding that reads them all, and then if you want more bits to a word, you make as many planes as you have bits in the word, and that was the main scheme that we used, and also MIT, by the way. There is another way of doing, which is less economical in leads, is the so-called word addressing. You make a decoder in here that decodes one word, and you make as many lines this way as there are digits, and this is the word address scheme, which, of course, today is the main scheme used in semiconductors. And so this is the photograph of one of our early memories, which the head of a match in here to show that you are a hero when you make it small, because what you want to store is information, not energy. And so then the signal, you always store much more energy than you needed to get a good signal. So the trick was to make it as small as possible. And then there was, at the time we were making this particular model, there was a craze about the decimal system, which turned out to be an idiocy, I think. But nevertheless, there was a craze, and so this is a decimal memory. And this is the 10,000-bit memory then that Morris mentioned at the beginning. And these things are magnetic switches, because even though this is 100 by 100, which is, of course, 200 leads and much less than 10,000, nevertheless, 200 is a big number if you have to drive each one by a tube. So we imagined a magnetic switch, which was also based on coincidence, so that it reduced it to 10 by 10 instead of 100. And well, in a sort of philosophical sense, the core is the idea of making things automatically, very fast, on automatic pressing machines, testing them automatically and assembling. And since you've made it and you've tested it, you are sure that you've got what you want at the bit. However, it seems intuitively from the very beginning that after all, why not use an integrated sheet or a wire or a plane or something? And so a lot of people, many groups in this country and abroad, tried to make a magnetic memory not with discrete element, but by some sheet. And so one of the attempts that we made was to make a ferrite sheet that was stamped with holes, and then metal was sprayed on the whole business, and then the metal was cut along these lines, and you can see that that metal produced a winding them all, because the current went through the walls of the tube from one element to the other, and then from this hole to this hole, and another square like this on the other side, so that this made a winding that linked all the holes in series. And then the other wire was just pushed through in a stack of cores, and that makes a much simpler construction. By the way, as very often happens in technology, another group thought of the same idea, namely Bell Labs, and they eventually made this, and they actually used this in some of the telephone systems. But there were also the ideas of using plated wires, of using etched permalloy sheets, many, many ideas. And there was a race then between integration, what we call today integration, and automation, that is making individual cores, but fast. And the automation always won. It was always cheaper to make the cores than to make anything else. And all of these attempts failed. I mean, the plated wire was perhaps the most celebrated of them, but it also didn't play out except in minor circumstances. And it's interesting though that in today's world of integration, the automation always won against integration, making an element one at a time and then assembling them quick. Well, the thing I want to say is that all the efforts weren't lost, because it's clear that in a plate like, in our project anyway, in a plate like this, if you make the current too strong in one of these holes, of course the flux around the hole will interfere with the flux around the other hole. And so that the question is, how close can you put the holes together before you get any interference? And then when we made experiments to do that, we found that, that this interference was very, very interesting on its own right. And so we invented a device that at one time was considered to be very significant, namely the transfluxer, which is a core with two holes. The idea here is that if you put a very heavy current in this winding, magnetize the whole business this way, then if you put a smaller current through this hole, which tries to change the magnetization around the small hole, why E won't succeed, because either you are trying to push the flux clockwise, and you can't increase it because it's already saturated, or counterclockwise, you can't succeed it either because it's saturated here. So therefore, you put an AC here and there's no voltage on the output. On the other hand, if you put a current through this winding that's strong enough to change the magnetization here, but not here, because obviously the magnetization decreases with distance, then you can put the magnetization like this around the two holes, and now if you put AC, why, it will couple perfectly well. You put AC here, it will couple. So here you are. It's a relay with no moving parts, with which stays latched one way or the other, and you can transmit fair amount of power rather efficiently through it. And then to boot, you can have it analog. In other words, you can reverse the some of the flux, but not all of it. Well, anyway, this invention turned out to fascinate a lot of people besides ourselves, and it turned out that some of the satellites were being built, and they wanted extremely reliable devices, and some of the early satellites had these things in. And the New York subways wanted control circuits which were absolutely foolproof. They used some of these and so forth and so on. I will also add, quite ironically, that the Russians read our papers, and they went in a big way to make logic. Oh, I have to say, of course, that since you can get an output from one, there's no reason why you can connect one to another and have all kinds of trees and all sorts of things. I just touched on the bare principle. But you can make a completely magnetic computers and logic circuits that way. Well, the Russians latched onto it because they were very slow on developing transistors. What happened is that the transistor was invented approximately at the time we were developing this, and when the transistor came in, of course, it made everything obsolete, vacuum tubes and magnetics. I mean, it's kind of silly to do logic this way when you could do it with transistors. But the Russians didn't have transistors, so they went in a big way. And later on, I had occasion to visit the Soviet Union on an IEEE trip, and I did see the place where they developed this, and they really went in a big way, and they made many advances with respect to our original ideas. I was really amazed how well they had developed the device, including automatic devices for molding them, testing them, and so forth and so on. Well, So much for the transfluxor. Well, now the idea of integration, though, it was still itching all of us. I mean, the idea that you have to make core planes one at a time. And so one of the ideas we took was to try to do it with superconductivity. And Dudley Buck at MIT invented a relay, superconductive relay, which is essentially two pieces of metal, one which is superconductive and another one on top of it, which when you put a current through it produces a magnetic field that destroys the superconductivity. And so he imagined a lot of things you could do. He was a great proponent of the idea. Well, our idea was to take the idea of the cryotron and make an integrated memory out of it. And this, you won't believe it, but has 500,000 bits. And it's a plate 3 inches by 4 approximately. And it did work. However, it had a number of problems of imperfections, lines that were not conductive, or shorted lines, or elements that were shorted in one place, or missing elements, or what have you. And so the problem was not so much with the cryoelectric aspect, which was tough enough, because of course you have to put this in liquid helium, but the problems were of the kind that the semiconductor integrated people experienced before. And we were sort of the naive people who tried to face up to all of these problems, plus putting this in liquid helium. So I'm just showing this, you know, as a little sideline that you don't always succeed, but you have dreams of making big things and integrated things. And this was about the most ambitious thing in the way of integration that was made before. But still, automation kept on winning. And it kept on winning mostly because you could make an automatic machine to test cores, where the cores just came in. This is one we made, but lots of them were made commercially afterwards, and came on a pin, and as it traveled on a pin, pulses of current were put in to test the core, and by the time the wheel turned a little ways, the circuits would decide whether it's good or bad, activated the relay and pushed them in one bin or another. The machines were made to test the cores at 100th a second towards the end of the reign of the core. And so that was one thing. And another thing was that people were more and more ambitious in reducing the size. This is an 80 mil core, and this is an 8 mil core, and this is a human hair here to support the cores. And of course you are a hero. The smaller you make them, the more you could put, the less energy it took to drive them. Well, now the next things I would like to say is that the invention of the transistor, of course, is fabulous. I mean, it's one of the greatest events that happened in electronics, and for that matter in technology. And one could then make a memory by using a number of transistors, which is what a static memory cell is today, with a flip-flop made out of transistors and access transistors to get to it. Well, in a sense, this is a gift of nature. You just take a chunk of mud and you mold it, and because there is a hysteresis, it does what you want. And so it's cheap, and but you still have to drive it by transistors at the edges. And here you have to go to the business of putting 6 transistors per bit. You have a lot of microgeometry. However, it's much better. It's faster, and you can read all of these goodies you get by doing that. And at the beginning, of course, this seemed to be extraordinarily expensive to do. But as the progress of integrated circuits improved, and as ideas were invented, such as using a one transistor cell with a capacitive storage, the dynamic memories of today, which use only one transistor, then of course the transistor memories eventually took over. And I don't have any slides of present-day circuits because you can see them galore any place you want. In fact, you can't help but seeing them in advertisements all over the place, so you've already seen these little things that have many thousands of bits stored. I was at a meeting just a month ago where I heard some papers, in fact 10 papers, 8 Japanese and 2 American, on a 1 million bit chips, dynamic RAMs. One transistor, one condenser per bit. And when you talk to people in the hallways, everybody and his brother is already working on 4 million bit chips. And so the question is, first of all, I would like, before going to further, I would like to say that to just put the development in perspective, here is the eyelet of the Selectron, whose diameter expressed in microns is this much. Here is the first core we made. Here is the core that eventually was the standard of the industry. And here, taking a little bit of that core in here, are the first integrated circuits. In other words, within that core, you had that, at each of those points was a bit. That's the grossest integrated circuits. And then today's integrated circuits at this scale look like this, where the spacing is 6 microns. Well, now, with a spacing of 6 microns, all the photolithography that you can, may I have the lights? All the photolithography you can do with light, and because the wavelength of light is roughly 1 micron, so that when you make things 6 microns, it doesn't really bother you, the fact that light is such a relatively gross physical phenomenon. However, as you well know, lots of people are working on spacing of 1 micron and submicron, and in fact in Cornell there is a national facility, submicron national laboratory, that tries to make structure smaller than 1, whose dimension details are smaller than 1 micron. And of course this is possible by using electron beam and X-rays. So perhaps I will terminate by sort of speculating about the future. In the first place, I'll take again the observation that Morris made at the beginning, namely how big a memory would you need? And when I first asked that question of von Neumann, he thought that 4,000 words would be fine. But I never believed that, by the way. And I always thought that the idea that you have to have a hierarchy of memories, that is to say that you have to have a tape and a disk and the core memory, and then there was a time where you also had a semiconductor, tiny one, which was faster than the core memory, so you had at least 4 grades of storage, that eventually what you want is a box that remembers forever, but you can access in 0 time, I mean, it's the kind of dream you want. Well, now, the question is, just how true is that desire for still bigger memories? And there I heard a paper also recently by a man from the artificial intelligence community who points out that the simple problem of analyzing pictures, which is not a very fancy problem really, already requires orders of magnitude more than we have. And then, of course, he cited many other problems you can do. And I don't think there is any question that you need bigger memories, faster memories, and you rather not have them mechanical. Well, now, the thing that's interesting, I think, if you contemplate 1985, 1986, that people are seriously thinking of making personal computers without disks. Hewlett-Packard has already one machine on the market that has enough internal memory that they don't need a disk. And so that the idea that you could have that single one memory and no mechanical memory to go with it, I think is very intriguing. Another thing that I think is amusing is that these things are now going under the name of solid-state disk. which seems to be an absurd way of calling them, but nevertheless that's the name under which they go. And I think that we are right at the threshold where small machine will be able to live without any mechanical machine at all. Now the next question you can ask, well, what if you want to mail a program or something? A floppy disk is mighty convenient. But there is really no reason why you can't mail it integrated circuits that has permanent storage in it, and the non-volatile semiconductor memory are making great strides. They promise a retention lifetime of 7 years at the moment because they are sissies, but there is no physical reason why it really shouldn't be any longer. So I wouldn't be surprised that you'll send a chip, and of course you'll be very smart with the combinations so that you don't need to plug many leads to use it. And so I will sort of reluctantly will end up by one more note of saying that a lot of people are giving papers nowadays and saying what is the fundamental limit of miniaturization, just how small can you make it until the signal to noise ratio gets to be such that you don't have enough certainty. And that's a very complicated question, of course, because now the error correcting codes are so good that you may tolerate a lot of imperfections that you weren't able to tolerate in the days when we were working. But it turns out that there are various limits given, like a tenth of a micron, or some people think maybe it's a hundredth of a micron, but it's in that general range. Well, of course, that's monstrously larger than DNA molecules. And I can't help, I hate the analogy of biology. I was always against this because I think that the art of computers has demonstrated is that invention is what made progress, not observation of life. And observation of life was always the wrong lead. You always have to invent. And I think in biology itself, it's the invention of how things might be that really made the big progress anyway, rather than observation. I mean, I'm a great believer of invention versus observation. But anyway, I hate to say that, but never to end on the note that the DNA molecule is enormously smaller than these predictions they make about transistor memories. And I would like to add that I have recently read that Schrödinger, who of course is the great physicist who founded quantum mechanics in many ways, considered the question of what life is. And he wrote a book, which I highly recommend you to read, a very readable book. Is called What is Life by Schrödinger. It's a very old book, in the 25s or 30s. And the main argument of that book, I think, is very pertinent, because he says this, that in order for the genetic material to store as much information as it needs to produce heredity with the complexity we know, the size must be very small, because in a sperm or in a seed it just must be very, very small. And yet, if you take thermodynamics, then you find a degree of certainty of where the state of that material, of course, gets to be less and less certain the smaller the element is. And if you put some numbers in it, you find that it doesn't jive. In other words, you can't make the element small enough, which obviously it is, since they are animals and plants that have heredity. It is that small, and yet by thermodynamics, it just isn't certain enough. So that's the puzzle he asked himself. And he concludes that the only saving feature is quantum mechanics. And it's only because of quantum mechanics and the fact that at the very low levels there are definite jumps that this is possible, and therefore the only structure that can transmit genetic code is a molecule. Pure deduction, no experiments, to my mind, a marvelous argument. And so if you take that argument and ask yourself, well, how small a memory element can I make? I think you could conclude it must be on a molecular level. That is, if I want to go much smaller than what transistors can do. But now you have to invent the method of storage, and worse, the method of selection, which is much, much more difficult to invent. So that's I will end on that note. Thank you very much.
Cylindrical cage inside, which is different than the model that you were talking here.
That's right.
Am I
That's
correct?
right. That
or
was my first
mistaken?
idea, that would make you the helical X and Y windings, two helices, with the idea that then the leads end up at the bottom conveniently. However, it turned out to be very difficult to build. We sort of were too ambitious. So the tube also had 1,000 bits, I think, instead of the first one, whereas this one has only 256. By the way, these eyelets were made on screw machines, and I'll say, just in passing, that a screw machine is a marvelous device. In other words, it's a device that for years already had a program where you put in, and then the machine gives you any screw you want, and it produced them at an unbelievable rate for practically nothing. It's a marvelous device, a screw, with enormous precision. I mean, we take it for granted in our civilization. It's the lowliest thing that you can imagine. But actually, it's a marvelous thing. And it took a lot of invention to make the machines. I didn't know that, by the way, because I thought it would cost a lot of money to make these eyelets. But we got them by the gross for practically nothing. They didn't have to modify the machines at all. They just put the program in and the eyelets came out.
What was the method of programming the screw machine? Sorry, this is a bit of a
Well,
digression.
it's mechanical, of course. Yeah, cams and things, yeah.
And it was invented 100 years ago.
That's right. Oh, that's right.
Swiss used it for
Swiss,
many
yes,
years.
the Swiss.
I'm interested in the ferrite, what you had to say about ferrites. I had the impression that the ferrites were invented in Germany during the war, or am I wrong about that?
No. What was invented in Germany was the permalloy, very thin sheets, not the ferrites.
Where were ferrites?
No, but magnetic tape was a German wartime invention.
That's
I
right.
thought, I'm almost certain, well, I don't know, I thought I had,
Oxide coating.
The
Oxide coating.
magnetic
The oxide
tape.
coating, yes.
Yes.
No, but
powdered iron, you're saying, but
Well,
not nickel.
the original ferrite was invented, if I remember well, in 21 by Philips. In 21,
1921.
yes, by Philips, and also by a Japanese whose name is Takai, and more or less independent inventions. And of course the ferrite made television yokes possible. See, television yokes, of course, have to switch the magnetic field very fast, and you can't lose much energy in it and so forth, so have to be cheap and so forth. So the television, the RCA, when I went to the RCA plant, they were carrying the ferrites in wheelbarrows, you know. And so they asked me, well, how many tons of ferrite are you going to sell with your memory? Yeah. And so I said, you know, the kilogram would be a better unit than a ton.
But I seem to remember that there were what we call dust cores, for radio frequency purposes.
Yes.
They were, I think, made of little particles embedded in some wax.
Iron particles in wax, yes.
Well, now, why did they come in instead of ferrites, if ferrites were available at that time?
Well, I can't tell you for sure. For one thing, the magnetization is higher in metals, of course. And so for transformer use, it's significant to have higher magnetization. And for another, I don't know that there was an industry right away to make the ferrites. Yeah. You see, that was a scientific discovery.
Also the frequency.
The frequency, yes. High frequency, yes, right.
but the ferrites can operate at different,
High-
there are
high
a wide
frequency.
variety of ferrites, but
Right.
they have different characteristics, but you can make them operate at very high frequencies.
Yes, but that was
Iron,
what
I
we
think.
wanted, you see,
Yes.
for radio purposes.
High frequency.
Yes.
Yes,
Well,
yes. Yes,
is
yes.
it possible that, when were you personally familiar with ferrites? Were you personally familiar with ferrites
Well,
before the war?
Yes, by the time I joined RCA, which was in 1935, ferrites was already there because they were already used in television yokes.
You're sure those weren't powdered iron?
I'm pretty sure they were ferrites. Pretty sure. I wouldn't swear to it, but
I-
I'm pretty sure.
Okay.
No, the irony, by the way, of the German very thin permalloy was that it was invented. It's just rolled, but the rolling was very clever, and it was invented by a Polish Jew. And and the fact is that despite of the fact that he was a Polish Jew, the Nazis didn't molest him because it turned out they thought it was so important. He later came to the U.S. Rather amusing incident, anecdotal story.
Do you remember when it was that Turing visited you and you had that conversation?
It was during the first Aiken Symposium, if you remember that.
Yes. Oh, relatively late, yes, I remember.
Yes.
Yes, yes.
Also, on the storage tubes, the whirlwind storage tubes always had a holding gun that
That's right,
sprayed
that's
electrons
right.
continually.
That's
You
right.
didn't mention that in your coverage of that part. Was that a
Yes,
just a
I did
refinement,
mention
or
it
was it
very
necessary?
fast. I did mention it, but perhaps too fast. Yes, they had a holding gun, and the thing stayed at zero.
What would have been the lifetime of a tube? Would it have been
Oh,
indefinite?
We never observed any to die. Of course, we didn't use them that many years, but that was
Johnniac went on a long
yes,
time.
long time. It was replaced by cores, not because they didn't work, but
Oh,
because
did
you
they put a core memory on?
Yeah,
Yes, they did,
yeah,
that's
yeah.
right.
because they could get more storage.
Yes.
But it wasn't. The tubes were still working.
Yes, there was a fallacy, an idea about the vacuum tube devices were not reliable, but it had a short life, but it's just not. I mean, look at your cathode ray
The
tube
cathode
today.
ray tube, yes.
Yes.
It's remarkable, yes.
You didn't say anything about a replacement flat cathode ray tube.
Well, of course, that's a different subject.
I know it's one you've been interested in.
Yes, that's the one that I was interested for many years. And well, the fact is, if you think of television and computers, eventually you produce a picture. And the quality of that picture is exceedingly important because that's the one human-to-machine interaction that you have. The whole industry is based on the cathode ray tube, which is a fantastic invention and works beautifully. But it isn't flat, and it isn't digital. And so that if you want to make a very high definition, for example, it's not so easy. I mean, you almost have to stand on your head to get 1,000 lines absolutely reproducible. So, I mean, in a graphic sense. So, there's a tremendous challenge.
And it doesn't really hold enough. I mean,
No, it
what we
doesn't.
want is a sheet that will fill the whole top of a disk.
That's right. It's not big enough, it's not flat, it doesn't have the right resolution, but it's the only thing there is. I mean, so to speak. Well, of course, the whole world by now realizes this, and of course, many teams of people are in Japan mostly, but in the U.S. and elsewhere too, are trying to make a flat display device with high resolution. And so have I. That was my personal dream for years. And we have made several attempts at it at RCA, one of which as way back as 1958, with using transfluxers, by the way, in electroluminescence. And more recently, there was a very big project to do it with a tube, but a flat tube, and that was quite successful. And of course, everybody is trying with liquid crystals nowadays. But the problem, to my mind, is not solved, and to my mind, it's a very good thing that it isn't, because inventors can have employment. Because it is the outstanding problem of electronics that's not solved. See, integrated circuits, people make prediction curves. They draw logarithmic curves, and they say that's going to be like this in 3 years, and it is like this in 3 years. Because there are so many people, and they think there are so many millions of dollars, so many teams, and they build on each other and all that. It's no longer fun. You know, you can't make a first-order invention. But in displays, it's the cathode ray tube that was invented in the last century. And then still it dominates the scene. So here you are, a fantastic challenge. I must say that I have spent, and I'm still spending a lot of time thinking of it. There are lots of things you can say about it sort of in a philosophical sense. First of all, if you make wires going running this way and that way, and you put something at the intersection to make light or control light, well, in the first place, you have lots of wires. That's the first thing you observe. The second thing you observe is that in the days where it cost $5 to put something on the end of the wire to impress the wire, namely a vacuum tube, why, that was hopeless. Because you had the 1,000 wires this way, 1,000 wires this way, 2,000 wires, $5 a piece, you know. And so, doing nothing else. Well, integrated circuits, for the first time, make it conceivable that you can make the circuits economically. So for the first time, there is a chance that even if you thought of something to put at the intersection, you could drive it somehow. But now you have to put something at the intersection. Well, the thing that's interesting is that the people who try to do this find that merely putting the 1,000 wires this way and that way alone, without anything else, is already difficult. So that the wires would be conductive, didn't absorb too much light. That alone is already a tremendous challenge. And now you have to still invent something to make or produce light, and more than that, something to do it selectively. That is, when you excite this wire and that wire, that's where the light is produced or controlled and nowhere else, like in the core. And so that there's plenty of things to think about. It's a really challenging problem.
Let's thank you and hope you make more inventions.
Thank you. Well, 1,000 wires.
Well, you mean for a television screen or?
Well, yes. Well, it's the television at the moment is 525, but everybody's working at 1,000.